Hello, I'd like to welcome you all once again in this yet another exciting topic on microprocessors. Particularly, we're going to focus on the concept of prime width modulation. Now, this is a concept that is very much important in power electronics and in general in electrical engineering. So I will take my time to look at what it is and how it is actually applied with microcontrollers in real life. So the first thing that we need to look at is the PWM. Okay. Now, what is PWM? Now, this PWM stands for prime width modulation. Now, if you think of prime width modulation, now think of this as a technique. It's a technique that is actually used to, it's a technique that uses a digital signal to control analog voltages. So that's what prime width is all about. So it's a technique that uses a digital signal to control analog voltages. Now, if we try to look at a prime width signal, it's a signal that may look something like this. So meaning that this signal contains the portion for which the signal is on and contains also the portion for which the signal is off and on, just like that. And this signal that we see right here, that is changing with time, it's a digital signal of on and off, and it is actually used to control some analog voltages. All right, now I'll actually just show you how this is possible, right? For example, we could be maybe before we go there, let's just try to appreciate the signal itself. What does it contain? So what does the signal contain? This digital signal, what does it constitutes? So this signal, you can see that it's some voltage value. It's some sort of a voltage or a digital signal that is having some high voltage value of 5 volts and then off 0 volts. So this is a really digital thing. But right now, I just want to show you that there's some terminologies that are associated with this signal. And it's very much important that you pick these terminologies. So the first part I would like to emphasize on it is that this signal has got what we call the on portion, and it has got also what we call the off portion. In fact, we normally say that it has got both the T on and the T off. Right? Now the T on, so it has got the T on and the T off portion. Now the other thing that is associated with this signal is that it has got what we call the TS, which is called the switching period. Switching what? Period. Now this signal has got a switching period, and this switching period is equal to the T on plus actually the T off. Okay, very much important that you understand this. Now the other component that we would want to look about this signal is that this signal normally it has got this portion which is always like a fixed period. Period doesn't change. And this is the T on portion, this is the T off portion, and it has got the T on and the T off. So now we can talk about the other component. What is the other component? The other component associated with this is called the duty cycle. Now, what is the duty cycle? Well, the duty cycle is the period for which the signal is on, for which the signal is on. Now, is what? Is on in relation to the whole period. Now, this is crazy, right? In relation to the whole period. Now, what I mean by this is that the duty cycle is actually, sometimes the duty cycle is given the symbol D is equal to the T on divided by TS. Meaning the portion for which the signal is on in relationship to the whole period, this becomes our duty cycle. And this duty cycle is actually T on over TS. And sometimes this duty cycle is expressed as a percentage. So you can say T on over what? TS times 100%. In fact, mainly it's expressed as a 100%. Now, I want you to understand that normally in prime width modulation, this period is actually fixed. So if the period is fixed, then what changes? So what changes is actually the duty cycle. This relationship T on over TS may be changing with time. Now I want to mention here what it means by that. So what we mean by when we say that the duty cycle is the one that may be changing. So if I have a signal, for example, that looks like this. Now, if you see here, the period for which the signal is on, which is the T on, T off, we can say that the way the signal is looking, it looks like it has got a 50% duty cycle. What does that mean? Well, what this means is that there is the period for which the signal is on is almost the same as the period for which the signal is off. In fact, if let's say this signal was about, let's say 20 milliseconds, or let's say that this signal was about 500 Hz. Now, if we say 500 Hz, what we mean? In terms of period, we're saying it's 1 over 500, right? Now, 1 over 500, guys, what is this? Okay, yeah, this is like what? So 0 0.0 about 0.002, right? 0.002, that becomes like our period. Now we can also say that the signal is actually on for 0.001 and it's off for 0.001. So now if we look at this signal itself as a period, if we look at this period, then we can say it has got a 50% duty cycle, because we can actually say that the period for which the signal is on, which is 0.001, divided by the period for which the signal is off, divided by the whole period times 100%, that becomes your duty cycle. So we can say that if we look at it, this is briefly about 50%, right? So now we can say that this whole signal has got the duty cycle of 50%, because it's actually on for 50% and it's actually off for 50%. but then the period is actually fixed. So what is changing is the T1 portion. So the T1 portion may actually move to this way. For example, now we can have a scenario in which now we have a signal. Now look at this. We can have a scenario in which exactly what we're talking about. But then the period could be fixed. This period could be fixed, but what is changing now is a larger portion of T on and a smaller portion of what? Of T off. And this could actually mean that we have maybe, let's say, a 70% duty cycle. It means that the period for which the signal is on in relationship to the whole period is about 70%. And so the duty cycle can be changing with time. So now guys, let's just try to appreciate what are the practical applications of this. Now we can look at the application of PWM. How do we apply it? Well, we can apply it in, for example, we can use PWM in trying to appreciate things like the light dimmers. We can apply it in drives, in trying to control the drives system by controlling the speed of a motor, for example, like a DC motor. Okay, so there's so many more applications, but now let's just try to look at what we mean when we try to apply it in, let's say, for example, like in light dimmers. Now let's just take an example. Now suppose I have a lamp, and this lamp is actually having a switch and it's connected to some kind of battery voltage. Now I'd like to explain PWM in this way. So I've got V here, which is the supply voltage, and I've got this switch right here. Okay, now suppose that let's try to get this example right here. Let's say that we have, this is our time, right? Now the question that I want to ask is that, well, if I close this switch, for some period, and then I switch off, then I switch on, you can see this is the switch, then it's on for some period, and I switch off and it's on for some period, I switch off just like, then I switch on like just like that. So this is like, think of this portion for which I am on as the switch is closed, and then off, the switch is off, and the switch is on, and the switch is off. So now what does that mean? That's this. So I'm just gonna put a ground here. So if I close the switch, depending on the amount of time that I use to close the switch, the current will flow and the lamp will just grow, right? But for how much? So in this case, I'm switching on and then on off, on and off, on and off. So if I'm switching on and off, the question that comes is that what is the average voltage that appears across the switch? Because then the switch never gets to light up fully. I mean, the lamp doesn't get to light up fully, because if I close the switch, the lamp comes on, but then if I open the switch again, the lamp goes off. So we're going to have a scenario in which we can just try to plot even just to check something else here. For example, if I look at the voltage, which is this voltage, so this is the PWM V voltage, and now let's look at the lamp voltage. So we have the V lamp. So how is the V lamp going to behave? how is it going to supply? So it's not difficult to see that if we close the switch, the voltage that is going to be applied to the lamp will only be up to this portion right here. So we can say that the voltage across the lamp will only appear for as long as the switch is on, right? And during this portion, the voltage across the lamp is not going to appear. The next time it's going to appear is when we now again close the switch. So we close the switch during this period. Now we can actually see here that the voltage across the lamp is actually behaving as we switch on and off the switch in that manner, right? So now the question that comes is that what is the average voltage? So we can see here that for sure that according to, this is the T on, so this is the whole period right here, the TS, and the voltage is actually behaving in a similar manner during this period, right? Now, if this is the case, then the question that comes is what is the average voltage that the lamp sees? What is the V average? What is the V average? Now, it's not difficult to see that if we now have to look at the V average, because now the V average is what the lamp is going to see. You can't say that the lamp sees completely, let's say if we have 12 volts DC, the lamp completely sees the 12 volts. You can't say that, because at some point we switch on, at some point we switch off. So now we find the average voltage. Now, what is the average voltage? It's not difficult to see that in this case we can find V average as equal to 1 over the switching period, which is actually this one, which is say TS. All right, then definitely we integrate between the known portions. Now, what are these? So there's 0 to somewhere like T on. So this is the T on portion, and this is the T off portion. During this portion it's off, and we're going to say V lamp. But then I know that the whole period, which is 1 over TS, but then now I know that the area under this period is only from 0 to T on, right? Okay, so if we actually look at this DTS, we can calculate, then we can say that V average is basically equal to the, we can see here that it's basically equal to 1 over TS, and we can say the V lamp multiplied by T on minus 0, right? So what we have now a very, very important equation right here. We can say that our V average is equal to the T on now divided by TS times V lamp. Okay, if we simplify it. So we can see that the average voltage that the lamp sees depends on this parameter right here. And this is the T on over TS is the same as the duty cycle V lamp. Because this is what we say, that D is T on over TS, the period for which the period that is on in relationship to the whole period. And this is the DN, so we can see that the average voltage that the lamp sees depends on the duty cycle, depends on the amount of time for which the period is on in relationship to the TS. So now what does that mean? It actually means that if, let's say for example, I have a V lamp equals 12 volts DC, and I have a duty cycle, a D of like 0.5 watts, 0.5, right? Sorry, 0.5. In this case, I have a D in which, let's say for example, the lamp has got a period of, let's say 20 milliseconds. And the time for which it is on is about, let's say 10 milliseconds. Then it means that the V average will be equal to 10 divided by 20 times the 12 watts. So that gives you that the lamp will actually see about 6 watts. So if the lamp can light to its full capacity at 12 watts, having a duty cycle of 0.5 or 50% will supply to the lamp about 6 watts. So therefore the lamp will not light to its full intensity, and that's a fact. All right, now apparently this duty cycle that we're talking about can change with time. So for example, we can have a scenario in which we don't have a 50% duty cycle, right? But we can say that the voltage, we can say, oh sorry, here we can say that now it's actually on for a long time. So even the voltage that is going to appear, the V lamp that is going to appear for this so much time, right? And there's going to be this off portion which is very small, and it's going to appear for this much time and the small portion. So here now we say that though the period is still a fixed period, and what is stretching is just only this component, but we have more here, more than 50%. And the more 50%, now think of a scenario in which we have a 20 milliseconds period, but then let's say that the signal is on for about, let's say 18 milliseconds in relationship to the whole period. Then definitely this is a bigger percent, maybe 80 or 70% or so, something like that. If you multiply this by 100, then that becomes that, and that becomes about 90%. So it's got a 90% duty cycle. Then it means that the lamp will give us something like the lamp then will give us something like the duty cycle of 18 over 20. So this gives us 90%, of course gives us 90%, right, which is 90 over 100, and that will give you about 0.9 times 12 volts, and that gives you how much voltage that will appear across the lamp. Now if we want 100% duty cycle, that is also possible, meaning that the whole period for which the signal is on, so if we have to do 100% duty cycle, it means that now between, if this is our TS, for example, which we expect to have the on portion and the off portion, we'll just have the lamp on, we just have the whole period taken, right? The whole period is taken, and if the whole period is taken, it means that we have constant voltage that actually appears across the load, and the voltage in this case, if this is PWM and this is our time, then we have also the V, what is this? The V lamp is going to be constantly on for that entire period. Now this is very important to digest, all right? And as you can see for yourselves that really this is some of the applications. Now, why would you want to do this? Well, this is a very neat technique. Actually, it's actually also used in motors. For example, if let's say for example this was a motor, for example a separated excited DC motor or anything like that, and then we have, think of this as a switch, and it's an electronic switch, like maybe a transistor or a MOSFET, and then this MOSFET has got a signal that is coming like this, or a PWM signal, and this motor is safely feeding from its battery. Maybe the battery has got a rating of 12 volts DC, and so we have a scenario like this. Now this signal that is going to be produced by a microcontroller, which we're going to discuss now as our next portion, it's going to cause this switch to close on and off depending on the duty cycle that is given depending on the T on over TS. Now, depending on how the on and off is taking place, this motor, we can regulate the speed at which the motor is actually moving. Now guys, you need to understand, now you're saying, okay, the speed, so now what does that mean? Now it actually means that the motor will be seen at one point. The motor could see, let's say for example, the motor can see 6 volts DC, the motor can see 8 volts DC, the motor can see let's say for example 10 volts DC, depending on the T on over TS. Now the thing is, you know there's something about the motor. For example, if you look at the separately excited DC motor, we all know that from as basic motor control, we all know that the speed of a motor largely depends on the armature voltage, right? So for example, we know that if I get my, let's say the KF, which is the motor constant, times the omega, which is the speed of a motor, that could actually mean the average of a motor, the average voltage across the armature or the V armature, minus the resistance, right, and the current or the on-state voltage drop across the circuit. And this we can actually make at steady state. We know that at steady state, we know that omega, which is the speed of a motor, could simply be given as IR over K, right, over K, which is the voltage constant, right, KF. Now, if you see here that the speed of a motor is actually direct proportion to the armature voltage, right? So it means that now if you look at the armature voltage is actually changing based on T on over TS of VS, which is our supply voltage right here, VS. In other words, our armature voltage is equal to the dVS, the V voltage times the duty cycle. So our A omega S is equal to the duty cycle times the voltage supply minus IR and KF. Now if we take KF to be very constant and the current here to be constant that is drawn by the motor and the resistance there, then it's not difficult to see that the speed now becomes the function of the duty cycle. If this parameter is constant and that parameter is constant, then the speed of a motor becomes the function of the duty cycle. And it means that if this D chops the VS at 0.5, then this becomes 6 volts. Then the motor actually is seeing 6 volts minus this, and the speed will be reducing. And if we increase the speed, if we increase the duty cycle, then we are increasing the voltage. And if we increase the voltage, we increase the speed. So this is just a technique that you need to appreciate, and it's very much important. So now let's look at how is this signal produced. How is the PWM signal produced, particularly in this case in microcontrollers, and what is the technique, for example, in Arduino to produce this very signal, which is the digital signal of on and off. Now guys, if we take a look at this from a point of microcontrollers and at Mega32, for example, you find that this is a very complicated kind of topic. It's not really complicated, but there's a lot of steps that you need to take to try to program it and have it up and running. And you can check my assembly video, my assembly notes, in which I was trying to show how fast PWM is done. But for now, let me just real quickly show you how microcontrollers would actually do. For example, particularly the Atmega family. Now, if you check the Atmega family, there are some specific registers. For example, if we look at timer 1 in Atmega 32, right? Maybe for example timer 1. In fact, let's not look at timer 1. Let's just look at, let's say, timer 0 or timer 2, something like that, right? Now we know that timer 0 and timer 1 in all Atmega families, these are 8-bit long. 8-bit long. So now what microcontrollers do, this is how they produce the PWM. So microcontroller would actually count. They count in a register called the TCNT. Now guys, you need to watch my videos on timers and counters, because these are some of the registers, the timer counter registers. So the timer counter register, what it does, we're looking at the TCNT 0, it counts from 0, it continues counting until when it reaches the end, when the counter, if the counter is 8-bit long, it counts. And when it reaches 255, so it counts from 0 to 255, right? About 255. When it reaches 255, we say that the counter overflows. It resets to 0. And then now, again, it starts counting from 0. In this case, if it is timer 1, it won't count up to 20 because it's a 16-bit timer. It's 16-bit in length. So it may count up to 65,535, right? So here it will start counting from 0, and when it reaches 255, well, there it is. It overflows. Counts, then what? Then overflows. Now, if we look at counting in normal mode, now there are two modes of counting, as I told you in Atmega 32. Even the Arduino, on the Arduino, what sits is an Atmega chip. Okay, the same concept here applies, and except that when it comes to programming, it's going to be a little bit different. But I have to explain from the Atmega point to make you understand. So this is a counter. This is how it counts. It counts. If we're counting in normal mode, we're counting from 0. In this case, we're dealing with timer 0, and then we overflow. And then we count, and then we overflow. Now, there's something about this in my controls. The time it takes for the counter to count from 0 to reach 255, and then it overflows to 0, back to 0. This is called the period. Think of this as the switching period that we were talking about. So it counts, it reaches that top end, and then it goes to 0, and then it counts from 0, again it reaches that. So this is the period for which the timer actually counts. Now here we're talking about the timer is counting in normal mode. If you're looking at it from the Atmega 32 and timer 1, we can actually even specify some of the registers. Actually, we can even say that this topmost registers is the ICR, for example, the input capture register, where we can specify what is the topmost before it overflows. All right. Now, when does the duty cycle, so it's this way of counting that actually produces also the PWM. I'm just going to show you right now what it means. Just let's go to the next page. So we're saying that microcontrollers, this is how they are counting. So they'll count. In this case, if we're looking at an 8-bit timer, it overflows naturally. And if we're counting in normal mode, this is what happens, it overflows. And this is the period, right? Now, if we want to produce a PWM signal, we can choose to count what is called in CTC mode. Now, the two modes of counting in normal mode and counting in what? CTC mode. Now, I'm using the Atmega 32 to try to explain this. Now, when we say compare, when we count in CTC mode, we are actually using the compare matches. Now, what do we mean by the compare match? Well, we mean that we can load a certain value in a register, and that register is called the output compare register, the OCR. So now this is the OCR that helps us to set our duty cycles. Now guys, I'm gonna explain just right now. So here it is. So if I draw this and I'll try to, I'm just showing you how we are producing this in a controller, like even the Amiga or the Arduino. So what it is that now when we reach 255, we're overflowing, and that is setting our period. But then if we use the CTC technique, now we are going to be having an OCR, which is called the timer, the output compare registers. Now guys, when we talk about this, when we say the period, now what is this period? This is high frequency. This is a sawtooth signal that is really running at high frequency. And this sawtooth signal is going to be compared with the value that we load in the output compare register in this case. So we're going to compare what we load in, so the counter, the TCNT, will be counting freely, and then it reaches the topmost and then it overflows. It counts freely, it reaches the topmost just like that. But we have what we call the output compare register. Now this output compare register, we're going to load the value. So for example, let's just take it easy that since we're counting from 0 to about 255, right? And so we want to produce an output signal of some kind. Now I want to show you how that output signal looks like. So for example, here we can, this is the analysis that is used now to produce what we call the PWM. Now we're going to get, by using the OCR register, and also by comparing it with the time it overflows, by loading a value into the OCR, because OCR will be loaded with the value. So what we're going to produce is a comparison between a constant voltage and a sawtooth signal, which is running at high frequency but then overflows at 255 there. Now what we achieve? So here is the point. When the value in the OCR becomes greater than the sawtooth signal, in this case, when the value in the OCR becomes greater than what the sawtooth is, we want to output a 1. So output high. When it's not like that, when OCR is less than sawtooth, output what? Output what? A 0. So here is the point. Just need to guide you a bit. So what is really happening here is that during this period for which this value I've loaded is present, I'm going to say that for this value, since the reference, this is our like a reference voltage. So in this case, our reference is greater than our sawtooth. So we're going to say here we have a high signal. And during this portion, we can see here that our sawtooth is higher than our reference. So here we're going to put what? A low signal. And during this portion, definitely it's higher. So we're going to have a high signal from all of that. And now here we're going to have a low signal as well, a high for that period. And this is exactly what we are actually having. Okay, and that becomes a signal that helps us to get our different duty cycles. Now let me explain how the different duty cycle really comes into being. Let me show you just now. Here is the point. So now we have, let me just show you. So let me just now say that this is our sawtooth signal. Now we're going to have our count overflows, count overflows, count overflows, count overflows. Now I'm going to show you, now we have two different signals. So there is, let's say that we're going to pick on the red, that is 1, and I'm going to pick on the blue, So let's say that now this line becomes our OCR, becomes our marker. So we have got, let's say that we have got one value that is indicating here, and now we have got another value that we want to indicate there, right? Now notice what is going to happen. So these two, this is like the previous value that I loaded, that was 0. Now this is a second value like OCR1. So now let's just try to compare what we see on the output by those two. What type of signal do we see? Now we can see here that if we look at the red, we have said that with the red we get a high signal during this period, and here we get a low signal because our reference is low. Here we have a high signal for this period, and we have a low signal for this period, and we have a high signal for this period, and we have a low signal for this period, and we have a high signal for this period, and we have a low signal for this period, right? This is what we see now. Here now we can try to look at what about now the blue. So let's just, the green. So if we look at the green now, this is what we have. Now you can see here that when I bring down for the green, I have this portion on, and I have this small portion off. I have, all right, so now I have this portion on, I have this small portion off, this portion on, I have this portion off. Now what's the difference here? What's the observed difference? Well, the observed difference is that this guy has got a lesser duty cycle, less duty cycle as compared to this guy. This guy may have, this signal has got more duty cycle, and this one has got less duty cycle. So now the more the duty cycle, the more the average voltage that appears across a particular system, and the less the duty cycle, the less voltage that appears. Now it's not difficult to see that when we move this OCR, the output compare register, from this point, now we shift it to the value that we load, the value that we load in the OCR. If we load a bigger value, it's like we're shifting this marker line that we see, and whenever we shift to the top, we are actually adding more in the duty cycle, the voltage. The switch is actually on for relatively higher time. Now to just show you, maybe help drive a point home as well, we can just draw something lower here. You can see here, if we draw something lower, then we can see here that the voltage here for which the period is on is very small as compared to the off period. So the off period becomes a little bit bigger, right, as compared to the on period, right? So you can see here we have the whole lot of this time. So by changing the value of the output compare register, we are changing the value of the duty cycle, which will effectively, or which will eventually affect the way we do our things, which will eventually affect the output voltage. So if it was now that same thing we saw about the motor, then we are saying if this is our switch, now very quickly, if this is my switch and this is my motor, then definitely what I'm experiencing now is that by virtue of having, let's say, 12 volts DC, if I now have these signals are the ones that are taking place, then definitely it's not difficult to see that we're going to experience different voltages at different duty cycles, because then now this is the signal that we're entering and it's going to be changing. Okay, now guys, I'm going to show you one of these days practically how this is implemented, but right now I just want to show you now how do we, since we appreciate the need that this could be used to chop our voltages and hence also control the speed of our motors, We can actually also use it for things like light dimming and things like that. PWM, prime width modulation. We can achieve actually also at different duty cycles. We can have low voltages, higher voltages, and things like that. So now let's just come to how do we implement it in an Arduino? How do we implement in the Arduino? Now in Arduino there are specific ports that have been assigned for PWM, okay, for prime width modulation. Not every port on the Arduino microcontroller is able to do prime width modulation. So there are specific ports that do that. For example, we have port number 3, 5, 6, 9, I think 10 and 11. These ports are able to do PWM on the Arduino, prime width modulation. In other words, the ports could actually toggle to do, you could actually use them to do the PWM command, to do the prime width modulation. Now, so these are the specific ports. Now they can output, you can actually output a PWM signal based on the following command that you can write. So there is a command, guys. You've seen so far the analog read command, but you've never known how to implement the analog write command. Actually, the analog write command is a command that we can use to output prime width modulation on the Arduino. So if I say, for example, if I say analog, it takes in two parameters. I'll show you what that is. So I'll write analog write, and then I will specify which pin. So in this case, I'm saying analog write 3, and then the next I'm saying on pin 3, and the next value that you provide here is a duty cycle. Analog write 3, then you specify that you are using, this is the duty cycle. Now the duty cycle here, right here, is a value that you can change between 0 to 255. Now guys, and I just want to mention here, think of this as the value that we are loading in the OCR. Remember I talked about the marker? So now what does it mean? So I've got 0, I'm counting from 0 to 255. But I can load different values. So I can have 127 loaded just right in the middle, producing 50% duty cycle. And I'll taught you how, why. And I can move this number to some, maybe like 130 or 150 or something like that. And that can produce an appropriate duty cycle depending on what I do. So here it is a clear indication right here that if you, so you are actually using different numbers right here. These are numbers that should range from 0 to 255. So if I, let's say for example, I load like let's say I say analog, right, then I say 3, then I say 127, right, because that's the duty cycle value. Okay, so of course 127 point something, right, because if counting starts from 0, then we have, okay, so if we load numbers between 0 and 255, so if we divide, so 255 by 2, then that is 1, then that is what, oh sorry, here you go, so that is 1, and that is 2, okay, that is 27, then 0.5, right? So so this approximately maybe gives us something like 50% duty cycle. So depending on the value that would want to load, we should have the appropriate duty cycle that we have, that we want. So if we load maybe 3 comma maybe 195 or 175, then we have maybe 70% duty cycle or something like that, right? So but then these are numbers that should range from 0 to 255, because then they belong to the duty cycle. And why are we saying 0 to 255? Well, we're counting from 0, and the time we're going to overflow is at 255. And this is the number, the marker that we're going to be loading different values, hence producing different voltage values across the pin depending on the duty cycles that we actually apply. Okay, so that's how it's actually been implemented in Arduino. So let's just look at an example. So for example, I'm going to show you an example in which we're going to have an Arduino, and what we're going to simply doing, we're going to try to control the speed of a DC motor. So what we shall do is that we shall connect to pin 3 of the Arduino, and we shall want to connect a potentiometer on A0. Now I'll explain why this will be important. So this is a potentiometer. I'm gonna put it there, and it's a variable resistor anyway. So it's going to be connected on A0, and what we shall be doing is that we shall use A0 right here to provide us with different values of the duty cycle that will be actually loading, and this guy will be connected to a transistor. In this case, I'll just draw it like this, but really what I'm using here is not really the type of transistor, it's a MOSFET. So we're going to use that, and this is our ground, and we're going to say that this is our motor, and this motor is feeding from 12 volts, and it's connected in this manner. Now what's the experience here? What's the big deal? The deal here is that we are going to be providing, so through the analog write, we shall take port 3, and we shall take the whatever value that we get. Remember the digital valve concept? Whatever digital valve concept that we get, whatever digital valve that we're going to get here, it will be the duty cycle, the on portion for which we're going to supply to this. And so we're going to be varying the speed of a motor by giving different values of the duty cycle that we're going to supply here. Now I'm going to show you how is this possible. Remember the temperature example that I showed you, how we were actually using the digital valve and all of that. So we're going to use the same digital valve to be the one that is going to help us to vary the duty cycles and hence control the speed of a motor based on the relationship that I showed you. Now guys, this is just the part A. I don't want the video to be so long, so I would like to stop right here. On my first two now, I'll show you how we actually write this code. Thank you so much for viewing, and I'll see you in the next class.